Swayam Prabha. Digital India. Educated India.
Throughout the day, there are 2 more lectures after this. So we will talk about some applications. So where do you use HPC? We'll try to give you some pointers what you can do next, right? So, well, this is a winter school on HPC, but everyone is into AI, ML, and now deep learning, right? So how many of you are, first interest is AI, ML, and then maybe HPC, second interest, right? Few of you. So the good news is, people are talking of convergence of HPC and AI. So your HPC knowledge is very useful even in AI. Yesterday, I think you might have heard Ashut, a lot of times he was talking of AI, ML, and the use of HPC in AI, ML. It's very useful, so just blindly writing a ML code is not going to give you that much performance. In order to analyze performance, in order to help you boost the performance, maybe some of the knowledge that you get in this field may be useful, right? So this is a kind of recent article, and they're talking of few problems which use AI. For example, detection of prostate cancer using AI. But the problem is the actual vehicle that does the simulation and prediction, everything, that is HPC based. So you need kind of knowledge of both domains in certain cases, right? And then they are talking of AI to predict climate, right? Okay, so with that, so what next? So some of you are asking, what shall we do next? So many of you are undergrads here. I've drawn this small, this part of a pie chart, which is like, you have some knowledge, maybe you have read something, you attend some winter schools or summer schools. You can think of taking a postgraduate, you can enroll in postgraduate program and enhance your knowledge further in a certain field of your choice. Of course, in masters, you don't work on a field, you try to get expertise on a range of subjects. So maybe systems, you're interested in systems, so you take more system subjects. You're interested in data science, so you take more subjects to strengthen your basic fundamentals, right? And then maybe you do a PhD and you become a full-fledged researcher probably. But it's still half circle. Half of the circle is unknown. There's a lot more to know. There's no end to knowing actually, right? All right. So all of you, I strongly recommend take a master's if you're undergrads, take a PhD if you're masters, right? So it's very exciting to be a student actually. Very few responsibilities, only your work. You have to just be a master. Your target is to be a master in your field, right? Right, okay. So now the question is where and how. That's again, depends on you, your maybe constraints, family constraints or other constraints. You want to stay in Bangalore, then look for colleges near Bangalore. There are IITs all over India. But then the only issue is if you want to gain expertise in a certain field, you should not only look for the institute, you should also look for the professors who are working in those institutes. And now looking at the profiles is not going to get you much. You may get an understanding, but then there are all these, winter schools, summer schools, and conferences that happen also in India. Maybe you can try to ask your college to send you there, to get more, to interact more with people who are actually working in a field of your choice, right? But I hope all of you know that you can give GATE and you can get into one of the IITs, maybe the top IITs, and you can, if you're already doing masters, you don't need a GATE score, you can just apply for PhD, there are interviews, written exams, and so on. Depends on the institute. Okay, and what after that? So this is a very small subset. There are tons of such companies who hire masters and PhDs. I have a lot of friends in Intel and AMD who are PhDs, okay? They hire PhDs, why? Because they are already an expert in that field. They don't have to do the training for them. Of course, the other option is academia. You can become a professor in a teaching institute or research institute according to your interest. But for this, of course, you definitely want to do a PhD. And sometimes it's also preferable that you do a postdoc, because in PhD you are like single-track mind. You have to solve a problem. Maybe your advisor has given you a problem, and you're trying to gain you're doing literature survey, and you're trying to get some expertise and trying to solve a problem. In postdoc, you're trying to kind of widen your little bit breadth, and probably maybe it's a good test bed to see whether you are fit for academics or not. In academics, it's slightly different from industry. Industries, most of them are business driven, or you will at least have a manager to tell you, maybe, that, yeah, this should be our goal, a broad goal. In academia, you have complete freedom in some sense. You can choose a problem, pick and select a problem that you want to work on. But today, we will be specifically talking of some of the research problems in HPC. So we saw this slide on the first day, right? HPC is like all throughout the stack, you can find problems to work on. So, but how to basically go about what people are already doing, that is the first step, right? And how do you do that? You look at the conferences, the top conferences in each of the part of the stack. It's not a complete list, it's just a subset. But some top conferences, you can look at the papers. Do not start with 2019 papers, you may have to look at 2000 papers that were written in 2000 to understand. Because if you start in 2019, they'll be referring to all the jargon that was built up in 20 years, and you will be like, oh God, what is this? I don't understand a line of it. Right? And so there are the technology always changes. So I think you might have heard of NVRAM and non-volatile memory, MCD-RAM, and so these are like latest technologies in the memory technology in the memory stack. And there are auto-parallel compilers that do auto-parallelization. Okay, there is research going on exascale operating system. Current Linux operating system, there are certain drawbacks when you want to use that for HPC systems, and especially when you're talking of exascale. Okay, then you can go even higher up and work on parallel algorithms, right? So I think he's not here, but so he was saying that, okay, so gather we can do this algorithm. Yeah, sure. You can think of new parallel algorithms that. So if your algorithm is better, good enough, then of course your compute time is expected to reduce. And then on top of that, you have to do certain optimization that you have been learning for a few days, right? So going forward, what you can do is you can kind of go through all the slides or think about what you have learned here, take up some pointers, maybe something was interesting to you, right? And I mean, this is just a very small subset of words that I just randomly put here, but you might have, maybe you got interested in certain aspect of all the languages and everything that we have spoken for these 5 days. So just, you can dig deeper into that maybe. Participate in events. There is one conference called High Performance Computing that happens yearly in India in December. So if you're interested in this field, make sure you try to maybe present a poster there. So they have a student research symposium that's only for students, right? Some of the student cluster competitions that are held worldwide. It's not, I don't think it's held in India, but there are 2 conferences that generally organize these events. Teams from all over the world can participate. Unfortunately, I don't think there was any team from India till date. China, Singapore, they have big presence there, and of course, US. So these are some of the resources. So the field is such that there is not a complete book that I can point you to, that this book is, in a nutshell, it will give you everything. If you want to look at papers, you can go to Google Scholar. There are so many online tutorials that are actually freely available. So one of the tutorials, I think, yesterday Bharat was using from this conference, supercomputing. So they generally put up their material online, many of them. So you can look into those, and then there are lots of online documentations. Okay? So on the first day, Ashish had mentioned that where is HPC required? There are many applications that use HPC, right? So now I'm only going to talk about HPC, and I'll give you one example of HPC application in a little bit detail. So HPC is used in many scientific simulations, right? I've just put two pretty pictures, maybe not so pretty, but so one is blood flow simulation on the right. On the right side, yeah, you're right. And the left side is crack propagation in a material. Now, these problems are very science domain specific, but what they use is C++ program, and they need to optimize that code. You need to run them faster. If your code is not optimized, you may be actually using 7 days of compute power, and you'll be doing what you could have actually done in 1 hour. That's what the goal was, to help you understand that optimization, code optimization is very important. Looking at the correct algorithm, looking at the correct way to code is very important, right? Then there are other simulations like, so this is some visualization of self-healing material simulation. So it's one of the top, it's published in Nature, so you can understand it's a very niche kind of work. So it's something novel in their field. And what they use? They use HPC, right? So typically, these scientific simulations, they are very compute intensive. For example, they solve large PDEs maybe, or they may be doing lots of force calculations which require like multiplication and divisions and so on. And they're typically also very long running. So the goal is to kind of help them optimize their code so that you can do a lot in a small amount of time. Some of the simulations, so for example, molecular dynamics simulation, the time scale is very small. It's in femtoseconds. So that's why in order to get a reasonable understanding of the problem you're solving, they have to solve billions of time steps. There's no other way. It's not for fun. It's just the science or the physics that requires to solve billions of time steps. So every optimization that you do, it's actually going to affect the runtime a lot, actually. So this is a snapshot from one of the very popular molecular dynamics code called LAMPS. And you can see you already know this, right? You have read this. So if you look through all these HPC codes, you will find snapshots of these. Maybe some are not good enough, some are good, and you also know how to figure out if they are good or not. And you have also looked at this, right? So that's what. Underlying all these codes are all OpenMP and MPI and OpenAC and CUDA, right? Okay, so today we are going to look into 3 case studies. So I'll talk a little bit about weather simulations. The next talk, Professor Rupesh from IIT Madras, he'll talk on parallel graph algorithms. Okay, this is not really scientific simulations, but it's an application of HPC where how you can use HPC for parallel graph algorithms. And then following that, in the afternoon session, we'll have Professor Aditya from IISc. He'll talk on using HPC for optimizing partial differential equations. Okay? All right, so getting started with weather simulation, right? So typically, when you do weather simulation, the hope is that you want to kind of predict what's going to happen if there's any critical event happening, other than temperature prediction for tomorrow or stuff like that, you also want to predict if there is any critical event happen. So for example, there was a lot of flooding in Chennai a few years back, right? And so if the goal is to predict much ahead of the actual event, right? So these pictures I tried to put in some like snowfall, heavy snowfall, some flooding and some cyclone and stuff like that, right? Okay, so which is why these weather simulations, they deal with actually hundreds of variables. So for example, wind velocity, temperature, precipitation, and so on. It makes the simulation very compute intensive, right? So this is one example of a cyclone which was, I think, or hurricane, they call it hurricane in the West. It was approaching this, the bay, the shore, the landfall. So what you are interested is, this is the eye of the cyclone. You see this? This is the eye of the cyclone or the hurricane, and they are interested that, everyone is interested to know when is this going to make a landfall. Depending on that, they take measures, preventive measures. So that is very important. It's a very important problem in all over the world, right? Okay, so now I'm going to walk you through some of, so how do you actually parallelize a weather code as such, right? So this is, let's say, we'll call this our domain of interest. Currently, this is our domain of interest, right? Part of Asia maybe. And we are here. We are actually interested in India. But if you just solve all the equations for India, you are going to not get the most accurate result, because the neighboring variables and everything, that affects, okay? The solution for the domain that you're interested in, you should typically look at a larger domain in order to get a better prediction. So what do, you have this large domain, and if you want to solve for this large domain, how do you go about it? Let's say I've given you 1,000 processors, okay? So how do you go about solving this, all the partial differential equations and whatever is there inside the weather simulation code? How should I solve that for this large domain? And you have 1,000 processors. Yes? Exactly, divide into, so basically grid mesh it, right? Or put some things like this, right? So divide this domain, so that's called domain decomposition. We are decomposing the domain, and now I will just give this one small chunk to one of the processors. Depending on how many processors you have, you will be able to divide this into coarser or finer resolution, right? Okay. So in these simulations, what they do is, so like I said, the values that you calculate in one of the grids or one of the processors, they are actually affected by the neighboring grids or the processors that own the neighboring grids. So then what do you need to do? This boundary that I have drawn, you need to exchange these boundary values. So which means you are doing something like 4 neighborhood exchanges with the 4 neighboring processors. Why do you do this? It's just the nature of how it's solved. It requires so it uses a 4-point stencil, so it requires the values from the 4 neighboring points, okay? And these are called halo exchanges, so which means you are having to do some communication, right, with the neighboring processors. And it turns out these are very expensive. They happen like 144 such exchanges are required per time step, okay? And so, which is why a lot of time is spent in communication, right? So could you think of a way, could you think of a way where you can actually reduce the communication time given your, your supercomputer, wherever you are running? In that network, so yesterday we heard of network topology, right? So given that network topology, can you reduce the communication time? And that leads to faster codes, right? So now, so here these two rectangles, you see these darker patches here, they are actually slightly lower pressure points and they call them depressions. Okay? Before cyclone, so you might have heard, right? So depression is forming in the Bay of Bengal region, right? Now we don't know if it's going to become a cyclone or not, but they are interested in tracking all the depressions as well because they don't know which one is going to become a cyclone, right? So which means that now your region of interest has, so of course you have the parent region of interest, but you also are more interested in these two regions. Now these two regions, they are at a higher resolution. So you had a certain resolution for the parent domain, a coarser resolution, okay? Now we want to simulate these at a much higher resolution, and that is why it becomes more compute intensive and more communication intensive. Basically, how do you optimize such a simulation is a good research problem. So what I said in the last slide was, I have a coarser grid here, which is at a coarser resolution I am solving the parent domain. And at a much finer resolution, I want to do this nested simulation. So finer simulation means more accurate prediction. Why is that? What is the fundamental difference between the coarser and the finer resolution? So I'll give you a hint. In the coarse resolution, what am I saying? I am here saying that this entire region is 1 point maybe, okay? But in the finer resolution, I am saying that I am further subdividing 1 point into many points. So I am saying that in the first case I said that my 25 kilometer by 25 kilometer, I will consider it as 1 point where I will be solving the equations. In the finer resolution, I am saying that 1 kilometer by 1 kilometer is my one single point, which means you have increased the computations by how many times now? What? 625, exactly. 25 square, you have increased the computation, right? So now you have made it more computer intensive and more communication intensive as a result, okay? So, yeah. Yeah, that is how they typically perform. The same set of operations are performed, but the resolution is different. That's all. The number of grid points that represent land area, that is different now. Okay? Yes, that's my next slide. Okay? So they do have to interact with the parent grid because you have now simulated the finer resolution grid, right? So now you have more accurate result for that finer resolution, those points. So the points that overlay with the parent grid, okay? Maybe I should draw this. So those points need to be communicated back, right? So let's say I had this points. This was my coarse grid, right? And now my final grid is somewhere I have the points here maybe. So in the final grid, I am actually also solving the points that are intersecting with the coarser grid. So I should pass those more accurate values back to the coarser grid so that they propagate. Okay? So now you can understand that because of this, you have a very interesting problem actually. So let me go back to this slide. So I said that here we are using 1000 processors. Now I have only given you 1000 processors. So what will you do about this final resolution? How will you use those 1000 processors again for the final resolution, which are even more compute intensive, let's say? You get the problem? No, but I have only 1000 processors. I have given you only 1000 processors. So you have two tasks here. One is the coarser resolution grid, and another is the finer resolution grid. So how will you use that 1000 processors for both of these? Can you tell me? And I also told you that the finer resolution values should be passed back to the coarser resolution. So they are not independent. you start with the left, this one, and then, but you have 1000 processes. You don't need to start with just one grid point, right? So you can still do, some of the, like, if you have 1000 processors and there was no final resolution, we were doing all these computations in parallel on the 1000 processors. But now I have told you that I have a separate set of, more compute intensive tasks. Now what should I do? Okay. But my question is, see, the course resolution also needs to be solved, and I have given you 1000 processors. Will you be using 1000 processors for the course resolution? And then I have another set of computations. So let's say, we'll call this, like, we have a parent and we have a nest. So I have total number of processors is 1000. Okay. And there's also a dependency. Actually, one time step of parent corresponds to 3 time steps of nests. Okay. This is the time correspondence, and you can see here the spatial, so there is some, so this is only part of the region, right? So only part of the, only few points will be communicated back to the parent. So that's the other aspect. So now tell me, I have given you 1000 processors, and if there was no nest, I'm going to run the course resolution on all the 1000 processors. I'll equally divide this into 1000 and I'll run them. Now I have a nest. So what should I do? Hold on, one at a time. What was your? So when I say processor, I mean one process is running on one processor. So for now, assume that I'm using this interchangeably. One process is running on one processor. These are very compute intensive processes. I'm not going to run more than one process on one logical core. Okay. Of course, you can, so you had an answer, right? Right, so that is one way. Your answer was also the same? We need to initialize the nested one from the coarser resolution, and every time step we need to exchange the data. Okay? So what he's saying is, Samuel, right? He's saying is, give something like, so 3, right? So 1:3 ratio, you can give some to the parent processes and some to the nest processes. Is there a problem with that? No, so they have to sync. Every time step they'll sync. So let's say this was my set of processors that was running the parent, and this is my set of processors which is running the nest. So I just do a sync up every time step. That's possible. But you said give this x and give this 3x. Is there a problem with that? What? What is the problem with data flow? What is the communication overhead? Pardon? Congestion will be there because? Are trying to send to X processes. Okay, good. And you had a second point? You had a second point or same point? Same point. Okay, that is one good point. The other good point is, the other thing is, so I told you this time step 1 and 3. Okay. But the computation, the number of computation, it doesn't directly, the total amount of computation and communication, if I want to say, it doesn't directly map to 1:3 ratio. Okay? So I just said that when the parent does one time step, the nest has to do 3 time steps. And I also said that if the parent resolution is 25 kilometer, maybe the nest resolution is 1 kilometer. Okay, so you have some ratios here and some, or in this case maybe, let's say, the parent was 3 kilometer and nest is 1 kilometer. But it's not the case that the nest if you give p processes or x to p and 3x to n, they are not going to complete at the same time. You see, there will be a lot of idling in one of these sets of processes, because what we assumed that because it takes 3x or whatever amount of computations more maybe, and I give them 3x more, it doesn't directly translate to the amount of time required. Okay? All right. So I guess you got a glimpse of some research problems. I mean, it's just a very small glimpse into some computational aspect in weather simulations. And one of the things I want to conclude with is typically these simulations are very data intensive as well. You produce, because now you have 1 kilometer, from 25 kilometer you have made to 1 kilometer, you are generating 625 times more data points also, right? So your data size has also increased. I am ignoring the fact that you need to take into account the neighbors. Can you explain more? Right. So I didn't say anything about the placement of the processors as such. So let's say you have the cursor grid and they are talking to the neighbors. Whichever process owns their neighbor, they will have to communicate. Yes. And actually that leads to another problem, that the neighbors are actually not physical neighbors. We talked about hops, remember? They are not physical neighbors. So that's another problem. Okay. But I only have so much time to talk about how are we solving this? So they don't actually solve the way you said. What they do is they use the entire set of processors for the parent, and again the entire set of processors for the nest, because anyway you have to exchange and you have to wait for the nest. So that way, so that's the current mode. But what you said is perfectly fine. That could also be done. Yes. No, we are running 1,000 processors. That is more than one processors. Fine. That also we are in. Yeah. Okay. That's what they are saying. 1:3 ratio. Yes, that's what these two people said. These two students said. And but the issue is, just if you look at the theoretical aspect that okay, this resolution is 3 times, so I give 3 times more, it doesn't necessarily translate into 3x time more time, the actual wall clock time. That's what I'm saying. Okay. But so currently these simulations are producing terabytes of data. And so they have become very data intensive as well. You are producing so much of data in your memory. Where are you going to store that data? Okay, 1 terabyte RAM maybe, but so there is the entire issue of this data movement, and not only for output but also for input, because you are also gathering data. You have a lot of observatories or observation points that's going to give you the input for actually doing these simulations, right? And so that's also huge now. Okay, so this is just a chart from one of the supercomputing sites in the West called NERSC. So they have this graph, a little old, till 2015. But what you can see is there's an exponential growth in data. This shows the amount of data being stored in their, on their storage. So users typically run their simulations and they keep on, storing data. So you see this increase is like exponential over the last decade or so. But what's the problem? The problem is our network bandwidth, I/O bandwidth, it's not increasing at a fast enough rate. Our compute has tremendously increased, right? So you have to deal with all this data. Okay, I'm saying that I'll compute at a higher resolution, I'll get better predictions. But the time to write into that disk or whatever else you're doing, that is not decreased by that amount that you want to, right? Okay. So So these are some closing slides. This is from Forbes, and this is not specific to HPC or anything. So they have this prediction that by 2025, we will reach 175 zettabytes. So basically, data is a huge problem, and therefore companies, they are also investigating more into the storage technologies, right? So we heard about, so we have this, so NVM, these are becoming more and more popular, so that you can store very close to the processor. Maybe you are going to reuse the data again, so no point in writing to the disk, which is still slow, right? All right, so with that, that's my concluding slide. So basically, there's tremendous research scope, and you can explore into each of the, the stack, whatever, based on your interest. But before I hand over for the quiz, I was requested by the ACM W Vice Chair to basically present this. So they couldn't be here, and this is target to mainly to the girls here. So we are a very small community, HPC is small, and women in HPC even smaller. But so they wanted me to show you some highlights or what they do around the year. So they have, so it's a very kind of large organization across the world. In India also there is some presence of ACMW. So what they do is they have some ACMW chapters, okay? There are some hackathons that they arrange. So ACM India grad cohort, I think 2-3 times it has already been arranged, then summer school and all that, especially for women. So there are some summer schools only for women. So I think these were their highlights for 2019, the current year. So they had a grad cohort where they invited the masters and PhD students mainly to interact with the academics or from industry, those who already have a PhD. And then they had a summer school for women on algorithmic game theory at IIT Gandhinagar. They had celebration of women in computing, and so basically they organize a lot of events. How to know about this? Basically join their mailing list or something. But the point is, try to participate in some of these events. You will get to know a lot, you will get to interact more, you will get some more pointers to think about what you want to do next maybe, right? So there are many chapters in India also, like 38 student chapters and so on. They also give scholarships to attend conferences. You don't necessarily have to present a paper, but you can ask for sponsorship if your institute doesn't sponsor you. Right? They also give some scholarship. They encourage you to attend the ACM conferences. So these are the top ACM conferences in many fields, for example, operating system and software engineering and ML and so on. Right? Okay. So this is their team. You can get in touch with, if you are interested to know more, you can contact Hina or Nutan. Nutan is a professor in IIT Bombay. Okay, so I am going to conclude here.